forget. Let's start recording. Now I'm recording. And there are two general applications of transformers. You either want to get more voltage than what's available from the line, in which case we call that a high voltage transformer. And the way we get those high voltages is by having more turns in the secondary compared to the primary, and that is a directly proportional. So if you have 10 times the number of turns in the secondary, you're going to get 10 times the voltage. The other application is a step-down transformer, where we want less voltage than what's available from the line, and the step transformer will do that. And we're very familiar with those types of transformers because when you charge your telephone or your computer, you're taking 110 volts from the line, you're passing it through the quotes-unquote adapter charger plug, and that adapter is really a little step-down transformer to give you the required voltages. In an X-ray system, the filament supply will call for a lower voltage. Filaments only work at 5 to 10 volts. So again, you need a step-down transformer. A second application of a step-down transformer is how do you vary the voltage on an X-ray machine? Remember that you have high voltage. You cannot change 100,000 volts to 101,000 volts without getting sparks. So we cannot change the voltage, the high voltage, in the high voltage part of the circuit. We change the voltage in the low part of the circuit, and we do it with a auto transformer. You provide the small increments of high voltage so that in the low voltage part of the system with a step-down transformer, and they usually use what's called an auto transformer. An auto transformer is a transformer with only one coil, and that one coil serves as both the primary and the secondary. You see that in this slide over here, where you have all these turns in the primary, but then you tap off, you pick off whatever fraction of those that you want, so that you have the full voltage that eventually will become presumably the full voltage on the tube, high voltage on the tube. But now you can, in this low voltage part of the circuit, right at the wall, the voltage coming from the wall, you can step it down to whatever voltage you want, and small increments here will give you the small increments of high voltage in the high voltage part of the circuit. So this is what we call the KVP selector. That's how you select the voltage. Okay, nothing to particularly try to memorize here. Just want to give you a layout of a very, very simple full wave rectified circuit. You have the auto transformer coming from the right from the line, and you pick off a certain amount of that here, and to feed into your high voltage transformer, which will then eventually, you remember you needed a rectifier. This is a rectifier bridge. Without going into details of how that rectifier bridge works, in the manual I've worked that all out for you. And then you put the voltage across, that high voltage across the filament and across the anode. So you've got your high voltage over, but notice that the KVP selector is over before you get high voltage. It's in the low voltage side. Part of that circuit that gave you the high voltage feeding into the high voltage transformer, you have to time it. You want to turn the exposure off at a given time, and you want to read how much voltage you have generated. So you have a KVP meter. That's a meter there. They also tap off some of those windings to feed the filament. Remember, the filament needs a step-down transformer. So the auto transformer also can serve that purpose. And here you have your filament feeding the filament of the tube. This is the filament transformer. It's a step-down transformer. And there's other nuances over here, which we needn't go into. You can read your MA over here. This is what we call a center tapped high voltage transformer. So you can put your MA meter right at the center there. That'll read the milliamperage that you have generated across the tube. Okay, so that's what a a circuit looks like a three-phase circuit, looks even more complicated. We needn't go there. This used to be a popular question on the old pre-core exam, ABR exams, where they would give you this a circuit and then put A, B, label certain parts of the circuit with letters, and then you were supposed to identify which by letter, which were the components, which was the transformers, which was the rectifiers, etc. They have not done that in the core exams, and I don't think they will. I'm just presenting this to give you a sense of how everything is laid out in a circuit and where each component is. Well, moving on. A rectification. I mentioned over here a rectifier bridge. I won't go into how it actually works, but I do want to mention why we want to rectify, rectify. And a rectification means a conversion of AC to DC, alternating current to direct current. Here is your alternating current waveform, nothing new over here, where as a function of time, we're plotting the sinusoidal variation of either voltage or current. I'm showing current with the letter I, okay? And you can see that this alternates between negative and positive. Well, that presents the problem that needs rectification. Here you see electrons going from the filament to the target, negative to positive. That's good. That's how we get high energy electrons, and that's how we get our X-rays produced. But that will occur during one part of the cycle, the positive half of the cycle. Now, what happens when the AC goes to the negative half, the B part? Notice then that there'll be a tendency of the electrons to flow from the target to the filament. That's not supposed to happen. You don't want to bombard electrons up against the filament. The filament can't take that kind of beating. The filament is just a thin wire that cannot take that electron bombardment. So we have to get rid of what's referred to as the inverse cycle. We cannot allow that B part of the cycle. And we have to rectify. Rectification is the conversion of AC to DC. You want to get rid of that negative part so that you only have flow in one direction, the direction of the filament to the target. So this is what it would look like. If we knock out that negative half cycle, now you see here the half-wave rectified system. And we define a ripple as being the variation from zero to a maximum, zero to a maximum. And in the case of halfway rectification, that's 100% ripple. It varies from nothing to everything back to nothing. That's 100% variation. There's an obvious limitation to halfway rectification. You're losing half the power. You're losing half the production of X-rays. Also notice that not only are you losing half of your electrical power, and that would yield ordinarily X-rays, but you're also going from zero to a maximum. So the voltage and the current keeps going back to zero. How much output do you have at zero? You don't have any output at zero. And how much output do you have where it's relatively low voltage and currents? You have very little output. So there's an output problem here. Not only are you silent for half the waveform, but even when you have the waveform, you keep going back to zero. So we have the full wave rectified. There is a electronic means by which you can rectify and flip over the lost part. Don't throw it away. Flip it up on top. Now you have output all the time. You haven't lost half the electrical power. You still have a ripple of 100%. It still goes from 0 to 100. So now that's going to be the limitation of the full wave rectified systems. It keeps on going to zero. What do you get when it keeps going to zero? You get very low outputs. And at zero, you get no outputs. So let's look at some terminologies. You know that we refer to the KVP, the voltage at the peak. That's the convention. We always talk about voltage at the peak. And for MA, we don't ever talk about MA at the peak. When we talk about MA, it's always an average MA. Okay, we never talk about MA peak. We talk about KV peak. Okay, and but now let's start identifying the limitations of full wave rectification and why we want to go to something else. Voltage and current goes to zero. I've mentioned that. The ripple is 100%. Well, that means then that your outputs are going to go down. If your output's going to go down because you don't have a full radiation production all the time, and when you do have radiation production, it may be very low amount of radiation output, and where you go near zero. Well, that means your exposure times are going to be low. I'm sorry, long, which means you're subject to motion problems. Notice that that your average energy is less. If you have a KVP up here at the peak, well, where is the average KV? Where is the average energy? It'll be here someplace, in the middle someplace. Well, if your average energy is low, that means then your average penetration is low, which means that your patient dose is high. Photons are not as penetrating if they have lower energy. So you have a patient dose problem in addition to an output and exposure time problem. So solution, three-phase rectification. Don't let the voltage and the current go to zero. That's what three-phase does for you. Let's trace that out. Here is your standard full wave. What we do is, rather than have a voltage and a current across the line all at once, like you see here, what if we break it up into three parts? You have the white part, and then a little bit later, you go down the line with another fraction. You split everything by three, so now you have two parts so far. You got the white going down the line, then you have the yellow going down the line, but do you see what we have just solved? The white is going to zero, but the yellow is going up. So where the white is going to zero, the yellow is supplanting it, is producing voltage and current. So you don't overall go to zero all the time. When you add these two up, you will get consistently high. But we go one step further, and we want to fill in this space over here. So now we put a third one. And that third one, then notice, will fill in that space. So if you, I've indicated the white one over here where it begins. Let's see what happens when we add all these up. When you add all these up, you will get consistently high, but notice nothing goes to zero. For instance, where white would have gone to zero along the dashed line, but now you have the green and the yellow adding in, so that you never go to zero, and you are consistently high, and and you have the sum of these three phases look like what I've shown. And if you count the pulses, here's one green, white, yellow, green, white, yellow. There's six of those. So we call this three-phase, six-pulse rectification. In one cycle, that's the, following one cycle, the white that started at zero here and goes through the full variation back to zero over here. And there are six pulses, and that turns out to be 11% ripple. It only varies from top to bottom by 11%, not 100% like we saw in full wave rectified. So we divide the wave into three phases, and then pass them down the line at slightly different times, and the net result is that your ripple factor will go down, your voltage and current stay consistently high, and now you've got more output. That was the mission you were trying to accomplish. Mission accomplished. And now I won't show you electrically how we can do it, but you can also get 12 pulses in a cycle electrically, and 12 pulses in a cycle will give you only 3% ripple. Very little variation from bottom to top. So these are the ones we have so far. We have the full wave, rectified, 100% ripple. Oops, come back. And the three-phase six-pulse with only 11%, and now the three-phase 12-pulse with very, very little ripple. Okay. Now, we've emphasized that that gives you the advantage of output, but how about the advantage of dose? What happened to the average energy? Up on top for single phase, you see the average energy, and the average energy is significantly lower than the maximum energy, the KDP. Uh, the average has to be somewhere between 0 and the maximum. So I've drawn in that red line indicating an average, not quite exactly in the middle, but approximately in the middle for our purposes. And three-phase, where it never goes to 0, notice the average energy is so much closer to the peak energy, the maximum energy. That means that the photons that you generate are in general more penetrating, and if they're more penetrating, more gets out of the patient and delivers information to the image plate, patient dose goes down. So we've seen then that three-phase gives you better outputs and better patient dose. Okay. And overall then, because we have better exposure times, then your motion problems go down. So better patient dose and shorter exposure times, less motion problems. Three-phase is the way to go. And all of our high-end equipment operate with three-phase. Okay. Here, I'm just showing you why your outputs are greater with three-phase. And again, it's we've already seen. Let me go back to it. We already seen the energy being the average energy being closer to the maximum energy. That not only gives you more penetration, but it also gives you more output, and gives you more output as we see over here, because the average energy is closer to the maximum energy, and but now also there's an MA advantage with output. Here is your average MA. There's your maximum MA. Notice that the average MA and the maximum MA are very close to each other, so that again, because you've eliminated the excursion down to 0, you're going to get more output. More output because your voltage is consistently high and your MA is consistently high. Okay? Enough said for that. But now I'm going to give you a third advantage. I've mentioned only 2 so far. There is 3. And the heat capacity of a system. Heat capacity of a system. Remember we mentioned and we showed you that three-phase allows you to rotate the anodes faster, 3 times faster, and we compared the charts, the heat rating charts, and we showed that there was a significant improvement in heat capacity. Well, that improvement was because you went faster on the anode rotation, but now also what I'm about to present. Uh, Here is your average MA, and let's say that you wanted an MA of 100. When you specify MA, you're always talking about average. So if I operate my tube at 100 MA, look what the tube is have to experience. The tube has to get 200 MA to give you an average of 100. So your desire for 100 MA with single phase means that you're banging the tube with 200. Because you go to 0 and you want to maintain the average, you just got to go that much higher than the average. So that means stress for the tube. It's stressed by 200 to give you a net of 100. But if you have three-phase, like I'm showing now, and three-phase 12 pulse, which gives you a 3% ripple, which is standard, well, 3% ripple means that around the MA, you're only going 3%. So the high is 101.5, 1.5% above and 1.5% below will give you a total of 3. So to get an average of 100, you're only stressing the tube to 101.5. In other words, the maximum MA that the tube experiences is essentially the same as the average. You do not bind the tube with 200 like you did with single phase to get the average of 100. Your average MA is so much closer to the maximum, and the MA is, the tubes are particularly sensitive to MA. So that means then that you can set higher MAs on the tube, and you can now radiograph bigger patients with smaller focal spots. Here's your advantage because on three-phase, the heat load is not as big as single phase. See right here, for 100 MA, you'd have to go up to 200 with single phase, but you're only going up to 101.5 with three-phase. So the conclusion is three-phase gives you better heat capacity. But if it gives you better heat capacity, then you can choose smaller focal spots, and which is what we've been saying all along. I had shown you this table before from the heat rating charts, and I show it again just to emphasize the big significant difference in numbers here. Single phase for small focal spot, 0.3, three phase, 5. That's very significant increase in your capacity to do longer exposure times that may be required by bigger and bigger and bigger patients. So another way of looking at that and why we have that enhanced heat capacity at three phase. I've already mentioned that maximum MA is essentially the same as the average MA, but another way of looking at it intuitively is that you are spreading out the heat more uniformly over the tube, and you don't have those big variations from you get 0 MA at one point on the focal spot, then you get 200 MA on the next very point on the focal spot. You got to go from 0 to 200, and but now you're going from 100 to 101.5 back to 98.5, which would be 1.5% less. So the full variation over which you are spreading the information out on the target is from 98.5 to 101.5, much more uniform deposition of energy. Well, and of course, if you have smaller focal spots, you got better image quality. So all these advantages, all of our high-end equipment goes there. Okay, how do you get three-phase? You got to use three-phase transformers. Three-phase transformers use 3 coils rather than 2 coils, and they look like this. This was a favorite question in the old board questions. What kind of transformers you use, and you were supposed to respond with these delta windings and star windings. This I present just to satisfy questions like, well, how do we get that? Get it? But I doubt that they'll be giving on the boards. It's more just basic background information. Okay, let's summarize this and move on. We've already seen that you get more outputs, you get better heat capacity, and you get better patient dose. Okay, those are the 3 major advantages. And under heat capacity, remember that means smaller focal spots, and that means better image quality. Okay. High frequency generators. This is becoming more and more popular, these types of generators, but I'm going to back up to portables and then build up to the high frequency generators. A typical portable machine is a high frequency generator. Let's see what we mean by that. Remember that portables are relatively small units. So you want a system that is relatively small that you can roll around the hospital. And the way they accomplish that is with a high frequency generator. And let's take a look at that. Rather than have the 60 cycles per second that we've been talking about, we go through an oscillator, and in a portable you go up to 1,000, and these days even more, 1,000 cycles per second. In a room, a full-fledged room rather than a portable, you go up to 5,000 cycles per second and more in hertz. Well, what does that do for us? If you have a first of all, you have in a portable machine, you have a small battery, so that you convert the DC from the battery to AC. Then you go through this oscillator, so that now you have a high frequency oscillation. And now, rather than rectifiers and whatnot, what you're doing is, what's a very special rectifier, what you're doing is, since you are such a high frequency, you can include in the circuit, the electronic circuit, a device that will make that system to paralyze at the high end, and that's what you see here on the right. The frequencies are so high that the system cannot follow it and will paralyze at a relatively high, at the higher frequency, but at the maximum. And then the ripple is of the order of your three-phase 12 pulse. It's somewhat little less, 2 to 3% rather than 3%. And but the point is that all of this requires very little equipment. It's a small package, which is what you want for a portable. And now this has been so successful that now we're putting it in rooms where the European manufacturers are tending, like Siemens is tending to produce these kinds of equipment because of their size advantage, their weight advantage, their cost advantage. They can be packaged very, very small and extremely small, actually. So that's another type of rectification. Just instead of 60 cycles per second, it's the going up into over into the plus thousands of cycles per second. Well, let's summarize this and put an end to this chapter. And there is your standard full wave rectified system with 100% ripple. We saw the 6-pulse system. We've seen the 12-pulse system. We've now, and the high frequency generators, which are very similar to it. And then you have a constant potential where there is zero ripple. These take a lot more electronics, equipment, and a bigger footprint, more cost. So you hardly see these in practice. In practice, our IN systems will have 3-phase 12-pulse. All CT scanners I know of, all interventional fluoro units I know of are 3-phase. And even now, just your standard general radiographic units are starting to appear very commonly with 3-phase because of all the advantages that come along with it. Well, this is my leading up to my last slide. Just a note in passing. We talk about the kilowattage on a machine. How much power does your generator generate, and how do we specify the wattage? Wattage is a measure of power, watts, the units of watts. And electrically, electrical power is defined as the voltage times the amperes, and the units would be in watts. So the convention is that the way we specify a generator, the kilowattage, the kilowatts on a generator is as per the equation. We take the voltage, but we usually work with kilovoltage, and then the convention is we multiply the voltage by the maximum amperage that the machine can take at 1/10 of a second exposure. That's how we specify it. The voltage times the maximum amps that the machine can generate without blowing up at 1/10 of a second. Okay, so as an example, CT and interventionals take the greatest power. We need power to generate those systems, and they're usually between 80 and 120 kilowatts. The next one in line would be general radiography and the fluorographic radiographic, standard GI fluoro units that can go up to 80 kilowatts. And then mobile units, which are the least powered, a maximum, let's say, of 30 kilowatts. So when you're in the business of buying equipment and specifying equipment, this is an issue. Usually at your level right now as residents, you walk into a machine, you don't have the slightest idea what the kilowattage is, and you don't really care what it is. You just want to see an image and have a satisfactory examination. Well, that's the end of chapter 4. I hope it wasn't too beneath you. I know it's the I try to fight my boredom as we go through that particular chapter. The next chapter is going to be much more interesting, and I'm going to go look for it. Chapter 5. let me let's see what we have. Okay, chapter 5. And as usual, when I start a chapter, many times I ask the question, where are we, where have we been? Where are we going? And we started in the X-ray tube, and we talked about the fact that you need voltage and MA and exposure time. And in the tube, you have Bremsstrahlung, the production of X-rays, that continuous distribution of X-rays, and characteristic radiation. And we got out of the X-ray tube. Well, before we got out, we talked about rectification and power and generators and whatnot. But now we're getting out of the X-ray tube, and we're going to go through the patient. And now the question is, what happens in the patient? And that's what this particular chapter, chapter 5, is going to address. We know that as radiation goes through that patient, an X-ray image emerges, and that X-ray image is invisible. And we eventually going to get to image modalities like a radiographic plate, a CT scan, or a fluoro, etc. And the role of the image modality is to take an X-ray image emerging from the patient and convert it to a visible image from which we can make diagnostic decisions. But right now, we're looking at what happens as the X-rays go through the patient. Now, everything I'm going to say is going to be generic. I could have been talking about what happens as radiation goes through lead or copper or aluminum. I'm going to, usually our focus is going to be the patient, so I'll use that as my focus. But the question is, what happens as the radiation interacts inside the patient? So, so let's get to it. Here you have X-rays incident on the patient, and then you have the image plate on the other side of the patient, and whatever happens inside the patient, if the radiation stays in the patient, that's going to give you patient dose, right? So that's certainly one aspect to it. But then we have a certain amount of radiation that gets out of the patient, and now the question is, of that which gets out of the patient, how much gets to the image plate? What comes out of the patient is your image information. And obviously you want to conserve that image information and efficiently convert it at the image plate to a visible image. And these are the three possibilities. As the radiation goes through the material, a certain amount is transmitted. That's what we were just talking about. That's what gets to the image plate and delivers information. But then you have radiation that never got out of the patient. That's absorption, and that is dose to the patient. But then there's a third possibility of radiation interacting with this material. You can scatter the radiation, okay? So that we have absorption, which gives us dose. We have scatter. The scatter gives us two major problems. Some of that scatter can arrive at the image plate and produce image quality, IQ degradation. That's bad. If some of that scatter reaches the image plate, plus some of that scatter will go out and affect people in the environment, in the area. So you, standing by your patient during fluoroscopy, are going to be exposed to that scatter. That's the reason we give you a lead apron and a thyroid shield and all the other lead protective devices in the fluoro room. That's why we put lead in the walls, to protect the people on the other side of these walls from that scattered radiation. It becomes an area hazard. So those are the three, and we say that, and we define the word attenuation. Attenuation is the removal of photons from the beam, and we can remove photons from the beam generally by two mechanisms. We can absorb the photons out, or we can scatter the photons out. So the word attenuation is really the sum of absorption and scatter. Now, we all use those words attenuation and absorption synonymously. Really, they're not synonymous. Attenuation is your overall removal. Absorption is a specific means by which we remove photons. Attenuation is always greater than absorption because attenuation is really the sum of absorption and scatter. Well, the transmitted beam, the beam that's not absorbed, the beam that does get to the image plate, identifies the tissues. Remember that as X-rays go through the various components of the material, and again, I'm emphasizing the material being a patient, that the that various tissues absorb radiation to different degrees. Bone absorbs a lot, and few photons get through the bone, so that bone stands out as a clear area, absence of photons. But air is just the opposite. Air will absorb very little, so that lots of radiation appears in the shadow of the air, and those regions of the image will appear dark, whether you're looking at a film image or whether you're looking at a video monitor image. Okay, there's your image information. It's the transmitted beam, and of course that transmitted beam can be corrupted by scatter, and then the overall image quality will degrade. But let's get to the actual mechanisms. We identified transmission, we identified absorption, we identified scatter, but how and when and under what conditions do these things occur? To understand that, we have to look at these various interactions. I'm going to start with coherent scatter, which is the lowest energy, lowest energy, and then I'm going to work my way up to photo disintegration, which represents the highest energy interactions. But let's go to coherent scatter. What is coherent scatter? In each one of these, I'm going to define a condition, and when that particular mechanism works. Coherent scatter only occurs if the X-ray energy is less than the binding energy. Okay, if you have an X-ray energy less than the binding energy, then coherent scatter can occur. And but let's look at that. The X-ray photon energy has to be less than the binding energy. But what is the binding energy of soft tissue? It's less than 1 keV. So these X-rays have to be extremely low energies, very low energies, for this to work. So right off the top, the frequency of this mechanism is going to be relatively low. And it's going to mean that coherent scatter is going to be, well, less than 10%. It's there, and but many times we can just ignore it or neglect it because other mechanisms are so much more predominant. So the first feature of this is that the X-ray energies have to be less than the binding energies, and the second feature is that the frequency of this interaction is going to be relatively low. But what actually does happen when you have energies less than the binding energies? Well, if you have an energy less than the binding energy, then ionization will not be possible. You cannot have ionization because to have ionization, you have to exceed the binding energy of those electrons. And if you have no ionization, then there's no dose, there's no bioeffects, there's no image information. Remember, we covered very early on that ionization is the basis for radiation hazard, number one, and ionization is the basis for the imaging effect, number two. And you're not going to have either if this coherent scatter interaction occurs. Well, if there's no ionization, what will happen? The X-ray photon will transfer the energy to the electron, but now you're going to have ionization. Okay, ionization is shown in this middle panel. I'm just showing it to you as the electron not being kicked out, but excited. and I've shown that with this these little waves over here. So you have excited the electrons, and then what's the final result? That you see on the right-hand side here, where the energy of excitation is emitted in the form of this red photon arrow here, and we call it the coherent scattered photon. It's scatter, isn't it? The X-ray came in horizontally in my picture here, but then goes off at 40 degrees, 45 degrees to the side there, so that the overall then is that the energy coming in is scattered off to some other direction, but it's the energy of that scatter as a very important relationship and really identifies the process that the energy emitted, the E subcoherent here, is exactly equal to the X-ray energy coming in. There's an exact correlation. Energy in is exactly equal to energy out. And that's why it's called coherent. By the way, it's also called classical scatter. Classical scatter. And we've already seen that the frequency is less than 10%. So essentially, this is a non-event. No ionization occurs, no dose occurs, no image occurs. The frequency is relatively low, and there's no loss of energy. The energy doesn't go into any other kind of process. It just gets redirected and goes off in another direction. Here's an example of that. If you have an X-ray energy coming in at 5 keV, but the binding energy is 10, right there, notice no ionization. You don't have enough to overcome the binding energy of 10. Well, that you excite the electron, sure enough, and the question is then, what is the energy of the coherent scattered photon? It's always equal to the energy that came in. And the energy that came in was 5, so the coherent scattered photon energy going out is 5. Okay, and by the way, that is emitted essentially instantaneously. It's a spontaneous thing, and so there is your coherent scattered photon, and I'll give you one a side note on that. I've shown you this picture where you excite a particular electron at a particular atom. In reality, just to give you the more truer picture, in reality, that excitation is spread out among all the electrons of the atom, and but that's a little harder to draw. So usually in the textbooks and in the discussions, you assume that one of the electrons got that energy, that one electron got excited, and that one electron emits that coherent scattered photon. Okay? Well, that's coherent scatter. It occurs at the very lowest energies. Let's not go on to the photoelectric effect. The photoelectric effect is one step higher in the sense of energy. What if you had an X-ray energy that indeed was greater than the binding energy of a particular atom? So now things are very, very different. Here you have the atom with a particular electron at a particular shell. X-ray comes in. The picture we have is that, yes, ionization is possible. And what was ionization? The removal of an orbital electron. So an electron goes off in some direction and with some kind of kinetic energy. And that electron will go into dose to the patient. All electrons, get that, all electrons, it doesn't matter how they are generated, all electrons always deposit all of their energy in the patient. They go nowhere. Electrons are non-penetrating. They will lose their energy and they will just go into a patient dose. Okay, the major mechanism of dose to a patient is the energy that the electrons had acquired that are totally absorbed in the patient. Okay, so ionization occurs, yielding kinetic energy electrons and going into patient dose. Down at the bottom of the slide, I've shown you the energy balance. In all of these interactions, always remember the condition and the balance. Remember that the condition for the coherent scatter was the incident X-ray was less than the binding. In photoelectric, it's more than the binding. In the coherent scatter, the energy balance was that the X-ray energy went totally into the coherent scattered photonic energy. But notice the expression we have for photoelectric effect. You did knock out an electron. It did take a certain amount of energy to produce that ionization. Come on. To produce that ionization. Okay? So you have to have a deposition of energy in the atom to knock that electron out, and then whatever's left over goes into the kinetic energy of that electron. And here's an example. We know that the balance of energy is the binding energy plus the kinetic energy. And what if the incident X-ray photon had 30 keV and the atom that's interacting with had a binding energy of 10 keV? Well, using our energy balance equation, notice that the X-ray, you want to find the kinetic energy of the electron. Well, the X-ray in was 30, the binding energy was 10. Well, the 20 would be the energy of the kinetic electron, the kinetic energy of the electron, and that would all go to dose. Okay, very simple expression. Total energy coming in is split between knocking out an electron and expending binding energy there, and then whatever's left over goes into the electron. And in this interaction, that incident photon is always totally absorbed. Poof, that photon disappeared. All of the energy goes into the act of knocking out the electron, producing the ionization, and imparting photoelectric, imparting energy to that electron, which, by the way, we call it a photoelectron. A photoelectron is an electron set in motion by the photoelectric effect. Okay. And we've already said, and I just want to emphasize again, that that electron will go to patient dose. And here I'm showing how it goes to patient dose. That high energy electron can knock out other electrons, which knock out other electrons, and it can keep on knocking out electrons as long as it has kinetic energy. And we call those multiple electrons delta rays. Delta rays. And all of these eventually will be absorbed and go into patient dose. A delta ray is an electron set in motion by another electron, delta ray. Okay, and these secondary electrons will produce ionization and knock out electrons of other atoms. So you have secondary ionizations. Okay. We continue with the features. We just seen that the initial interaction is that the photons knock out an orbital electron. And if they knock out an orbital electron, what happens consequent to that? Well, remember back in X-ray production where we had the incident electron coming in, knocking out an orbital electron, and we created a vacancy? And what happened subsequent to the creation of a vacancy? Other electrons from higher up in the atom in higher orbits, those electrons fell into the vacancies in the lower orbits and gave up the difference in binding energies in the form of characteristic radiation. It's going to happen again with photoelectric effect. It doesn't matter how you create a vacancy. It doesn't matter how you create the initial ionization. If you have a vacancy in an atom, electrons from higher orbits will tend to fall into those lower orbit vacancies and emit characteristic radiation. And that characteristic radiation is always equal to the difference in binding energies between the orbits that these electrons are falling across. And out goes characteristic radiation. So another feature of the photoelectric effect is you produce characteristic radiation. And just like we saw in X-ray production, that you can have multiple characteristic radiation is produced because you can have multiple transitions between orbits. The same thing is going to apply here. Here we see a transition from L to K orbits. Out comes the characteristic radiation, characteristic of that energy difference. But now, as we have that vacancy moved up to the L, then a electron from higher up will fall into that. We're giving you another characteristic radiation. And then you're going to have another characteristic radiation when you have that cascading of electrons from one level to another level, so you can have those multiple characteristic radiations. And in every step, those characteristic radiations always equal to the difference in binding energies. Point to take home. Okay, and here is a numerical example. If you have a binding energy in the K shell of 30 and the initial vacancy was created in the K shell, okay, then the L to K would be, in this case, 30 minus 5, which is 25. The M to L would be a 5 minus 1, which is your 4. And then from infinity, a free electron, unbound electron with binding energy 0, it would be 1 minus 0 or 1. And just emphasizing that if you add these up, you get 24, 25 plus 4 plus 1, 30 keV. That's exactly equal to the energy that you had originally invested to produce the vacancy, the original binding energy of the K shell, the 30. And so whenever you have this cascading effect or this transitioning of electrons between orbits, the sum of the characteristic radiations always equals the initial binding energy. That's conservation of energy. Whatever energy you had started out with when you produced the ionization, well, you're going to get it back in the form of characteristic radiation. And there's all kinds of different possibilities. You could go from infinity to the K, where you get one characteristic energy photon with the full amount of 30, or you can split it out 25 and 5 with this process, or this 29 plus 1 in this process. See, there's various ways of the electrons to transition between orbits, but in all cases, each characteristic radiation is equal to the difference in binding energies. And in all cases, when you add up the characteristic radiation from any given pathway, they always add up to the initial binding energy. Okay? And I had given you a statement when we were looking at mammography and the choice of target and filter materials in mammography. I had made a statement when we looked at that, which I did not prove at the time, but I'm going to prove now based on the photoelectric effect. That statement or principle I had stated was any material is transparent to its own characteristic radiation. And but before I prove that, I want to refresh your memories, the background of that statement. We had just chosen molybdenum, for instance, as a target material. And molybdenum choice was based on the fact that it had characteristic radiation. When the electrons interacted with the molybdenum at the target, it produced characteristic radiation, which was approximately 20 keV. But it also produced a whole range of other energies. You know, it was a Bremsstrahlung production of energy. So you had low energies, you had high energies. The low energies produces dose. The high energies degrade image quality, degrade subject contrast. So we were looking for a way of eliminating those low energies and high energies, but allowing the good radiation, the 20 optimal energy keV radiation to get through. And that's when I came up with the idea, let's match the filter material to the target material. And we have a Moly-Moly combination. If we have a higher energies and we have rhodium targets, we would match rhodium-rhodium. And the idea was that when you match a filter to its target, then the characteristic radiation from the target goes right through the filter with no absorption. The filter is transparent to its own characteristic radiation. Wow. That means that you can knock out the low energies, you can knock out the high energies, but you're allowing all the good radiation to get through. Well, our time is up, but look at the proof down here. And it's just based on the fact that if your X-ray energy is 20 and your binding energy is 20, and here's your X-ray energy, 20, your binding energy is 20, well then how much kinetic energy is available for the electron? 0. And if the electron cannot have any kinetic energy, it can't move away. And if it can't move away from its orbital position, it's not ionized, which means that this interaction can't occur. The photon goes right through and does not interact with that electron, and cannot produce the ionization, cannot set that electron in motion, so it cannot occur. So that the interaction cannot occur, and if it cannot occur, the photons incident on the filter go right through without performing that interaction. It will interact to eliminate the low energies. It will interact to produce that to reduce the high energies, but it will not interact to remove the 20s from the beam. Okay, the 20 kVs, a good radiation from the beam. Well, our time is all gone. Are there any questions? Otherwise, we'll move on and pick this up at our next session. You all have a good Thanksgiving, and we'll see you the next time. Have a good one. Just click end meeting.